we just talked about the eigenvalue and eigenvectors, right? So here is we're giving one example. Okay. So you can see that. Okay. For matrix A like that. Okay. So its characteristic equation is a determinant of A minus lambda I. It will look like this. And because it's 3 by 3, so I think like you guys all know like how to calculate the determinant. Okay. So it's going to look like this. So after you expand it, okay, and the solve it, okay, it's going to be this one. Okay, so you have like lambda is either 0 or 1. Okay, if lambda is 1, okay, you plug in 1 here. Okay, so it's going to be this is 3 minus 1 is 2. 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2. So it's going to be 2. You can see the color is 2, 2, 2. Negative 1, negative 1, negative 1. Negative 2, negative 2, negative 2. So, obviously, the rank of this matrix will become 1. So you can solve it. You get like, 2 different vectors. Okay. And so for this eigenvalue, you have 2 different eigenvectors. I probably should correct myself. This is like I should say eigenspace that correspond to this eigenvalue can be expanded by these 2 vectors. There are many eigenvectors correspond to this eigenvalue. Okay, but they can all be spanned by these 2 vectors. Or you can say the dimension of this eigen space is 2. Okay, and then if you let lambda to be 0, okay, you solve this and you will get like one single eigenvector 1, 1, 1, which obviously that means the eigenspace, like the dimension of the eigenspace correspond to the 0 eigenvalue is dimension 1. Okay. And few things to mention. First, like this example obviously shows that for one given eigenvalue, we could have more than 1 eigenvectors. Second, okay, previously I told you guys, okay, for characteristic equation, okay, you could have like a real eigenvalue, you could have a complex eigenvalue. But in this example, you could say this is a simple example because all the eigenvalues are real. Okay? And the third one is that, okay, when we say eigenvalue, eigenvector, be careful. We say eigenvector cannot be 0. But eigenvalue could be 0. Okay, let me go back. Okay, if there exists a non-zero vector x such that ax equals lambda x, here I have never said that lambda cannot be 0, right? Okay, the only thing I say is the corresponding eigenvector has to be non-zero vector. Okay, so this example happens to show you, okay, we have a 0 eigenvalue. Okay, and then obviously a non-zero corresponding eigenvector. Okay? As for like the straightforward. So this is yeah. This shows like the process. Okay. For example, when lambda is 1, okay, this is like a minus lambda I is 1. So try to solve this homogeneous system of linear equations. So you get like this. So I think like pretty straightforward. The other case is lambda is 0. Okay. So I'll skip these slides. If you are interested, then you can check out by yourself. Okay. Another example. Okay. Another given matrix A. Okay. And again, we try to calculate the characteristic polynomial of this given matrix A, which is determinant of A minus lambda I. So you get this one. So again, I mean, you expand it and you get yeah. So you have like lambda. The root will be 0 and 1. Okay, and when lambda is 0, it's is it the same? Or is different with similar? I think it's very, very similar. So I'll skip the calculations. So, so there are some properties. These properties are trivial. Okay, trivial. That A be an n by n matrix, and lambda is a scalar. The following statements are equivalent. Okay. The first one, lambda is an eigenvalue for A of A. Okay. The second one, A minus lambda I, okay, x equal to 0, has a non-trivial solution. Obviously, if lambda is eigenvalue, according to the definition, okay, it must have a corresponding non-zero eigenvector. So the second statement is given. If the second statement is given, obviously the null space of A minus lambda I is not just zero vector, obviously. If that's the case, I mean, you don't, the lambda wouldn't be an eigenvalue, right? Okay. I mean, so, and then A minus lambda I is singular. I mean, again, according to the definition of singular, okay, well, that just means like the determinant of A minus lambda I is 0, right? So these two statements are equivalent, okay? And that also means like A minus lambda I x as a non-zero, non-trivial solution. So that's why like, all these statements are equivalent. I mean, this, even though these are, we say these are property, but they are very straightforward, very easy to see. Okay, not much to really talk about. But the following properties are interesting and also require proof. Okay. The first one, if lambda 1, lambda 2, blah, 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 lambda k are distinct eigenvalues of an n by n matrix A with corresponding eigenvectors x1, x2, blah, blah, xk, then x1, x2, blah, blah, xk are linearly independent. Okay, here, okay, there's one important thing to, you know, to bring your attention to, okay? These lambda I are distinct eigenvalues. Okay? It is not like, okay, for any eigenvectors, okay, n eigenvectors, Okay, they are linearly independent. No. Okay, if their corresponding eigenvalues are different, then they are linearly independent. Okay? Actually, yeah, let me finish the proof and then I can tell a little more about this. Okay, how do you prove this? By the way. Again, I mean, if you need to prove something, okay, we always start from the definition, right? So let's consider the definition of linearly independent. And we start from just two eigenvectors. Assuming their eigenvalues are different. Okay, we start with two eigenvectors. So we consider x1, x2. Okay, given x1, x2, such that, okay, ax1 equal to lambda 1 x1, and ax2 equal to lambda 2 x2, and lambda 1 and the lambda 2 are different. Okay? So let's consider two vectors. We start with two vectors with different two eigenvectors with two different corresponding eigenvalues. Okay. So we want to show these two vectors are linearly independent. Then basically we need to do a1 x1 plus a2 x2 equal to 0. Okay, and we need to show this equation, the only possible case for this equation to hold is a1 equal to a2 equal to 0, right? That is like according to the definition of linearly independent, right? So let's say if we have that, we need to derive, eventually we need to derive a1 equal to a2 equal to 0. That's our goal. Okay. So what we can do is we can apply a on both sides. Okay, a, this one, equal to a, 0, right? Okay, we apply a on both sides. I'm too lazy to copy this again. Okay, and then you can expand, right? This will be a1, ax1 plus a2, ax2 equal to, well, a0 is still there, right? And then ax1 is lambda 1 x1, right? So we have like lambda 1 a1 x1 plus lambda 2 a2 x2, right? So far so good, right? Right? And then let's try to consider this equation and this equation. Okay. You can can multiply the first equation by lambda 1, right? And the subtract the second equation. Then the first term, lambda 1, a1, x1, cancel out each other. So it becomes like a lambda 2, so lambda 1, a2, x2, minus lambda 2, a2, x2, equal to 0. But then basically lambda 1 minus lambda 2, a2, x2 equal to 0. We know lambda 1, lambda 2 are different, right? Lambda 1, lambda 2 are different. So this one is non-zero. x2 is non-zero, right? Because the x2 is an eigenvector, so it can, the eigenvector, well, is considered non-zero, right? So the only possibility is a2 is 0, right? So you can do similar thing to show a1 is 0 too. Okay, then we have okay, so we can easily show that you know for two eigenvectors, if their eigenvalue, corresponding eigenvalues are different, then they must be independent. Okay. We can expand this one to 3. Okay, basically it's simple. Okay, and then by we can use induction, assuming this property holds for k distinct eigenvector and distinct corresponding eigenvalues. Then we just add one additional eigenvector in here, assuming that the corresponding eigenvalue is different from previous k eigenvalues. Then, okay, we can easily show that, okay, we can easily extend this property. Okay, so I will skip that part. Okay, I mean, if you are able to extend from like 2 to 3. If you are able to do that, I mean, extending this product from k to k plus 1 is pretty much similar. Okay, so so this is the interesting property. Okay, for eigenvalues and eigenvectors. And from this theorem, one thing you can see is that, okay, as long as your eigenvectors have different eigenvalues, they must be independent. Okay, if you have, so here, okay, even though the theorem say like, okay, so it's k, so basically like any k value, as long as these eigenvectors, okay, these k eigenvectors, they have distinct eigenvalues, they must be linearly independent. So this is a very interesting problem. The second one is even more interesting, but it's a little bit tricky. Okay, if A is an n by n matrix, the trace of A denoted as trig TRA, okay, is A11, A2 plus blah plus A and N. First, we define that. Basically, it's just like the trace of a matrix is the sum of the diagonal elements. Okay, that's the definition of trace. Once you know that, once we have this definition, so the second, the theorem is very interesting. Okay? If n by n matrix A is with n distinct eigenvalues, lambda 1, lambda 2, blah, blah, lambda n, okay, then, okay, determinant of A is lambda 1 times lambda 2 times 4 times lambda n. Okay, the determinant of A will directly be the, the product of these n distinct eigenvalues. And the trace of A, okay, will be equivalent to the sum of these n eigenvalues. So these properties are very, very interesting. Very, very interesting. How do we show that? Again, we need to start from the definition. So you can see that okay. We have like this eigenvalues. So how do we calculate eigenvalues? How do we solve eigenvalues? We are doing this thing, right? We are doing this, right? We try to solve the characteristic equation to get the n roots, right? This is how we solve the eigenvalues, right? So can we be more specific? A11 minus lambda A12 A13 A1 A21 A22 minus lambda A23 This is how we can calculate the determinant, right? Equal to 0. I mean, why do we need to write down this thing? Because determinant is calculating determinant is a kind of complicated process, right? I mean, according to the definition, how do we calculate determinant? You start from a given row, right? A given row. For example, you start from here. Then you get this one times the determinant of here. Right? Okay, and then you minus this one times determinant of getting of this row. So this column, this row, right? So it's a recursive process, right? It's a recursive process. Okay. So that's so this one, I mean, you can tell it's going to be A11 minus lambda. Okay. Times M11, right? And then minus A2. Sorry. Guys still remember how we calculate the determinant in the determinant like structure. Like this is like a recursive definition. Right? That M, remember how we define that M? M is like you get rid of M1 is you get rid of the first column, the first row, okay, and the rest